Hello everyone. I would like to uh, provide a proof of Gauss's law to you. Uh, it's very simple. So suppose um, we have we have divergence of E, a divergence of T equals to 0. This means the electric flux field is conservative. So under this condition, you might have something like this, right? A small pile. Oh. So the field's going in, the electric flux going in is the same as the electric flux going out. Say, for example, this is DS1, which represents uh, the flux going through this cross section. So this, under this condition, uh, divergence of D must be 0. D here is equal to the electric flux. And you know the formula. So, and the area, yeah, here it is S. So the area should be like this. So under this condition, we know that D, let me see here, it's better to use E S1 is exactly equal to, so suppose the area here is delta S1 and the area here is delta A1. So now under the condition divergence of D is 0, then we have this conservative uh, result. So now think about this. If this little area delta S here is not just a delta S, it's not an independent delta S. Instead, it is a part of the perfect circle, perfect sphere. So this is the perfect sphere with radius r. And on the other hand, this delta A1 here is the section of an Gaussian enclosure, and this Gaussian enclosure is not a perfect sphere. It can be irregular shape. It can be something like this. So So this is the section we are considering. So under this condition, if we can apply divergence of D over this section, this little portion, we can equally apply divergence of D being equal to 0 to other area of the same sphere. So in other words, right, if you can apply to the same to this portion of the sphere, you can equally apply it to the other portion. So this could be delta A2, and the flux here could be d of A2. So similarly, we can extend the same analogies, the same uh, technique, and we can apply the same treatment to other portion of the same perfect sphere. So for example, I'm going to do this. So here we can have another delta S. Two. So this is delta S 1, and this is ds2. So the flux here is dA3, and the area here is delta A3. So I'm going to cross out this unwanted text here. Yeah, it's not unwanted, but it's just confusing. So we are now dealing with the condition. Divergence of D is 0. So literally, you can even extend the same equality to all other portions of the same sphere. This is the perfect sphere. And this irregular shape here is the Gaussian enclosure. So on the left side of the equation, we can write EI. The echelon may be the same because we are not dealing with the same three-dimensional space. So we have this, and here we can do the same, and A2. And again, we have to emphasize this must be vector because the E field, the direction of E doesn't have to be the same as the direction of area. So it's better for us to highlight the fact that it's a vector, and this is a dot product. Dot product. So now, wouldn't it be better if we write this statement into an integral? And instead of using delta SI, we use delta S. So, by the way, I have to highlight, right, this is E of SI. E of SI. This is E of AI and E of AI. So you never get confused. So this is I, I. So now rewriting the left side, the right side of this equation, we get E of A and then dA. And remember the dot here. Yeah, dot product. Now, taking a look on the left side, which is an expression for the whole sphere. The electric field magnitude should be the same everywhere on the surface of the sphere. So E of S can be taken out of the integral, and the vector could be removed. So we use ds. So integration of ds is obviously the surface area, total surface area of the sphere. And the right side can be copied as before. So now, if you take a look here, we are going to use Coulomb law to evaluate this electric field. So if I memory serves me well, by Coulomb law, the electric field on the surface of this sphere can be calculated as 4 pi, 4 pi, I'm sorry, right? We run out of space here. So I am going to rewrite it in here, yeah? So I am using the arrow and point it to here, yeah? This is an indication that I am going to continue in this area here. So on the left side of this equation, we have epsilon and E of S. E of S can be calculated by Coulomb law, which is Q over 4 pi epsilon r squared. And the integration of D of S. So we have the area. We are going to sum up all the small portion of delta S together for the whole sphere. So literally, this sphere is just like a bubble inside the Gaussian enclosure. It has its own surface, and its total surface area is 4 pi r squared. So the left side, the right side of the equation will remain the same. So if you simplify the left side, 4 pi got cancelled out, 4 pi get cancelled out, r squared get cancelled out. So you get Q. And the right side is A. So obviously, we have proven the Gauss's law. So I hope this is clear enough. Okay, thank you. Bye-bye.